This is the EdExcel A-Level Further Maths Paper 2, covering the core pure content, and it's from the 2021 series. Question number 1. Given that z1 equals 3 lots of cos of pi over 3 plus I sine of pi over 3, and z2 is equal to root 2 lots of cos of pi over 12 minus I sine of pi over 12, for part A, we have to write down the exact value of the mod of z1, z2, and the argument of z1, z2. First of all, you will notice we have a minus here. Ideally, we want a plus. How can we get that? Well, we know that minus sine of theta is the same as sine of minus theta, and we also know that cos of theta is the same as cos of minus theta. So we can rewrite z2. And so, for part A, we begin with z1 equaling 3 times by cos of pi over 3 plus I sine of pi over 3. And also z2 is equal to root 2 multiplied by cos of minus pi over 12 plus I sine of minus pi over 12. We have rewritten z1 and z2 such that we have a plus before the I sine of theta. So when we come to calculate the value of z1, z2 modded, this is the same as z1 modded multiplied by z2 modded. The mod of z1 is 3. The mod of z2 is root 2. So what we end up with is 3 multiplied by root 2. And to calculate the argument of z1, z2, that result is equal to the argument of z1 plus the argument of z2. The argument of z1 we know is pi over 3. The argument of z2, that's minus pi over 12. And so the argument of z1 times z2 is equal to pi over 4. Now for part B, we're given that w is equal to z1, z2, and that the argument of w to the power of n is equal to 0, where n is a positive integer, we have to determine the smallest possible value of n and the corresponding value of the mod of w to the power of n. Well, if w is equal to z1, z2, that means for part B, w is equal to 3 root 2 multiplied by cos of pi over 4 plus I sine of pi over 4. And so w to the power of n, that's equal to 3 root 2 multiplied by cos of pi over 4 plus I sine of pi over 4, all raised to the power of n. And so if we simplify this even further, we have 3 root 2 to the power of n multiplied by cos of pi n over 4 plus I sine of pi n over 4. And that's just using de Moivre's theorem. Now, we know from the question that the argument of w to the power of n is equal to 0. So, if the argument of w to the power of n is equal to 0, then what's inside the bracket must be a multiple of 2 pi. And of course the reason that works is because sine of 0 will just be 0. So we can have n equals 8. And that's because if n is equal to 8, we have 8 pi over 4, which is just 2 pi. We want a multiple of 2 pi, so n equals 8 works. And then the value of w to the power of 8 modded, that will equal 3 root 2 to the power of 8. And if we work this out, let's just use our calculator. We have 3 root 2 all to the power of 8, which is 104,976. Question number 2. We've got the matrix A, 4 minus 2, 5, 3, which represents the linear transformation M, and we have to prove that for the linear transformation M, there are no invariant lines. We begin by assuming that the point xy and the point x prime, y prime lie on the line y equals mx plus c. Y equals mx plus c, we'll call equation 1 for now. And if that's the case, we have 4 minus 2, 5, 3 multiplied by the vector xy, and this will be mapped onto the point x prime, y prime. But remember, the point xy and the point x prime, y prime lie on this line. Now, if we state what x prime and y prime are, x prime, well, let's just multiply up these matrices. We've got 4 times by x minus 2 times by y, and we also have 5 times by x, and then we add on 3 times by y. The result of this is x prime, y prime. And so we can state then x prime is equal to 4x minus 2y, and because we know that y is equal to mx plus c, you can see then that we have x prime equaling 4x minus 2 lots of y, and y is mx plus c. And if you want to expand all of this and simplify, gathering the x terms together, we have 4 minus 2m lots of x, and then we have minus 2c. Similarly, y prime, we have 5x plus 3y, so we have 5x plus 3y. Now we know y is equal to mx plus c, so we've got 3 lots of mx plus c, and if we tidy this up, the x terms, we've got 5 plus 3m of those, and we have 3c as well. Now, because we know x prime and y prime lie on this line, if I call this equation 2 and this equation 3, what we can do is substitute in 2 and 3 into 1, and that's essentially because x prime and y prime lie on the line. So if y prime lies on this line, we replace y by y prime. So we have 5 plus 3m lots of x plus 3c. This is equal to m multiplied by x prime. And we know what x prime is. That's 4 minus 2m x minus 2c. And then we have another plus c. And if we try to tidy all of this up even further, we have 5 plus 3m x plus 3c equals, well, here we would have 4m minus 2m squared x, and then we add on c minus 2mc. And if we compare coefficients, comparing the x terms, we have 5 plus 3m of them on the left hand side, and 4m minus 2m squared on the right hand side. So we've got 5 plus 3m equals 4m minus 2m squared, from which we can see 2m squared minus m plus 5 equals 0. And if we compare the number terms, you can see On the left hand side we have 3c of those, and on the right hand side we have c minus 2mc of those. So we have 3c equals c minus 2mc, and so 2c is equal to minus 2mc. Let's call this equation 4 and this equation 5. Now if we pay attention to what the question is asking, we want to show that there are no invariant lines. And if there are no invariant lines, let's see what values of m we have over here. Let's see what we get for the discriminant. So from equation 4, if we use the discriminant, we've got minus 1 all squared, minus 4 lots of 2, lots of 5. We end up with minus 39, and this is less than 0, so we can see there are no real values of m, and so we can therefore conclude equation 5 would have no solutions because there's no real values of m. So what can we conclude from this? We can conclude that there are no invariant lines. Question number 3. We're given f of x is equal to the arcsine of x, where x is in between minus 1 and 1. For part A, we have to determine the first two non-zero terms in ascending powers of x of the Maclaurin series for f of x, giving each coefficient in its simplest form. Well, if we go to the formula book, the information for the Maclaurin series is given here. Let's just highlight it. This is how we evaluate a Maclaurin series. Now what I've done here is just written out that Maclaurin series formula. So if we have f of x equaling the arcsine of x, we need to first of all find out f of 0, and f of 0 is equal to the arcsine of 0, which is quite simply 0. The inverse sine of 0 is 0. Now, if we were to work out what f dash is, it's the standard result. If we go to the formula book, and then under the differentiation section, the differential of arcsine x is equal to 1 over the square root of 1 minus x squared. So f dash of x is equal to 1 over 1 minus x squared square rooted, which for convenience I'm going to rewrite as 1 minus x squared to the power of minus 1/2. So if we work out what f dash of 0 is, that's 1 minus 0 squared to the power of minus 1/2, which is 1. We have the first non-zero term equaling 1. If we work out what the second derivative is, using the chain rule, we first of all multiply by the power, and then we have 1 minus x squared. We then subtract 1 from the power, so then our power becomes minus 3 over 2, and then we multiply by the derivative of the bracket, which is minus 2x. the minus and the minus cancel out. A half times by 2 is 1. So we end up with x lots of 1 minus x squared to the power of minus 3 over 2. And so if I evaluate f double dash of 0, we have 0 lots of 1 minus 0 squared to the power of minus 3 over 2, which is 0. So we need to work out another derivative. F triple dash of x, well, here we can use the product rule. We have x multiplied by the derivative of 1 minus x squared to the minus 3 over 2. Well, here we need to use the chain rule again. So we multiply x by minus 3 over 2 lots of 1 minus x squared to the minus 5 over 2 times by minus 2x. And then we add on the derivative of x, which is 1, multiplied by 1 minus x squared to the minus 3 over 2. And if we tidy this up even further, well, we have x times by x, which is x squared. And then we have the 3 over here because the half and the 2 cancel out, so do the minuses. So we have 3x squared lots of 1 minus x squared to the power of minus 5 over 2 plus 1 minus x squared to the power of minus 3 over 2. And so f triple dash of 0 is equal to 3 times by 0 squared multiplied by 1 minus 0 squared to the minus 5 over 2 plus 1 minus 0 squared to the power of minus 3 over 2. It turns out here we get 0 plus 1, which is 1. And so if we substitute back into this formula, you will find f of 0 is 0, f double dash of 0 is 0, so we have x lots of f dash of 0 plus x cubed over 3 factorial multiplied by f triple dash of 0. And so therefore, using the Maclaurin series, we have f of x equals x lots of 1 plus x cubed over 3 factorial lots of 1. So we end up with x plus x cubed over 6. And now for part B, we have to substitute x equals 1/2 into the answer to part A and hence find an approximate value for pi. We have to give our answer in the form p over q, where p and q are integers to be determined. Well, what have we just found here? We found an approximate for the arcsine of x. That's what we've just found in part A. So if I substitute in x equals 1/2, then the arcsine of 1/2, that's equal to, using what we have on the right hand side, 1/2 plus 1/2 cubed over 6. And so the arcsine of 1/2, that's pi over 6. So we have pi over 6 equals, and here, if I substitute in 1/2 into the right hand side, we have 1/2 plus 1/2 cubed over 6, which is 25 over 48. And so pi then is equal to 6 lots of 25 over 48. So if I multiply this by 6, we get 25 over 8. So therefore pi is approximately equal to 25 over 8. P is 25. Q is equal to 8. Question number 4. In this question, you may assume the results for the sum of r cubed from r equals 1 to r equals n, the sum of r squared from r equals 1 to r equals n, and the sum of r from r equals 1 to r equals n. Now, for part A, we have to show that the sum of the cubes of the first n positive odd numbers is n squared lots of 2n squared minus 1. Well, for the cube numbers, we have 1 cubed, which is 1, 2 cubed, which is 8, 3 cubed, which is 27, 4 cubed, which is equal to 64, 5 cubed, which is 125, 6 cubed, which is 216. We could continue. Now, what is this question asking for? The question is asking for the sum of the first n positive odd numbers, and that's key in this question. We want the sum of the cubes of the first n positive odd numbers. That's another key word over here, the positive. So what are the positive odd numbers? Well, we've got 1, and then we have the 27, then we've got the 125, and then we could continue. So what sum do we need to work out exactly? Well, we've got the positions. We've got 1, 3, 5, and then we could continue 7, etc. And then we can cube all these. What is the nth term over here? Well, rather the rth term. Well, this sequence of numbers has rth term 2r minus 1. So what exactly do we require? We require the cube of these numbers. So we require the cube of these numbers and then add the results together. So we require 1 cubed plus 3 cubed plus 5 cubed plus 7 cubed, continuing. So in general, we require the sum of all this from r equals 1 to r equals n. So what we can conclude then is we require the sum from r equals 1 to r equals n of 2r minus 1 cubed. And so the general term over here is 2r minus 1 and then cubed. So we want the sum of all these, as we see here. So how could we evaluate all of this? Well, 2r minus 1 all cubed, we first of all need to work that out. If we work that out, we have the sum from r equals 1 to r equals n, and then if we use the binomial expansion, we have 3 choose 0, 2r to the power of 3 minus 1 to the 0 plus 3 choose 1, 2r squared minus 1 to the 1 plus 3 choose 2. Well, let's just write this on a new line. We have 3 choose 2, 2r to the power of 1 minus 1 cubed plus 3 choose 3, 2r to the power of 0 minus 1 cubed. So what I've just written down here is the sum of 2r minus 1 all cubed. And so if we work this out, we have the sum from r equals 1 to r equals n of 8r cubed, and then we have minus 12 r squared plus 6r minus 1 and we can split this up even further. We have the sum from r equals 1 to r equals n. Well, rather, we've got 8 lots of this result. Of r cubed. Then we've got minus 12 lots of the sum from r equals 1 to r equals n of r squared plus 6 lots of the sum from r equals 1 to r equals n of r minus the sum from r equals 1 to r equals n of 1. And what we need to do is work out all of this. Now if we go to the formula book, we can use the summation for r squared, that's this result here, and we can also use the result for the summation of r cubed. So if we evaluate this, we have 8 multiplied by, well, for r cubed, we've got a quarter n squared, n plus 1 all squared. So we've got 8 times by 1 quarter times by n squared lots of n plus 1 squared. Then we've got minus 12 multiplied by, well, the sum of r squareds, that's the 6th n lots of n plus 1 lots of 2n plus 1. So we've got minus 12 times by 1/6 times by n lots of n plus 1 lots of 2n plus 1. And then we add on 6 lots of the sum of r's. Well, that's 6 lots of a half times by n lots of n plus 1. And then we subtract off the sum from r equals 1 to r equals n of 1. We subtract n. So let's continue to work all of this out. 8 times by a quarter, that's 2. So we've got 2n squared, lots of n plus 1 squared, minus 12 times by 6, that's minus 2. So we've got minus 2n, lots of n plus 1, lots of 2n plus 1. Then we've got 6 times by a half, which is 3. So we add on 3n, lots of n plus 1, and then we subtract n. Now if we expand a little, we've got 2n squared, lots of n squared plus 2n plus 1, minus 2n, lots of, well here we get 2n squared plus 3n plus 1 plus 3n squared plus 3n minus n. If we expand again, 2n squared times n squared, we've got 2n to the 4, then we add on 2n squared times by 2n, that's 4n cubed, then we add on 2n squared, we then subtract 2n cubed, then we subtract 6n squared, subtract 2n, add 3n squared, add another 3n, and then subtract n. So if I tidy all of this up, we've got 2n to the 4 minus n squared, which simplifies to n squared, lots of 2n squared minus 1. So that's all of this simplified. Now for part B of the question, the sum of the cubes of 10 consecutive positive odd numbers is 99,800. We have to use the answer to part A to determine the smallest of these 10 consecutive positive odd numbers. So for part B, the key in this question is to realise we're not starting at r equals 1 and finishing at r equals 10. If I actually work out what that is, the sum from r equals 1 to r equals 10 of 2r minus 1 cubed, this is equal to 10 squared times by 2 lots of 10 squared minus 1. So 10 squared lots of 2 lots of 10 squared minus 1, we get 19,800. Now you can see here, that's not equal to 99,800. So what we've worked out here is the sum of the first 10. We've worked out the sum of the first 10 odd cube numbers. We don't want that. So let's just write that down. So we are not starting at r equals 1 and finishing at r equals 10. We don't know where we're starting, but what we can do is start at some position x. Remember, r equals 1 represents the first position. So if we let x equal the position of the smallest of these 10 consecutive positive odd numbers, we are starting at x. The one after this is x plus 1. Now we're cubing these as well and adding them together. The one after this, we've got x plus 2 cubed, and then we could continue. And the final term, we've got 1, 2, 3, and the 10th term will be x plus 9, all cubed. That's essentially what we're working out here. And the result of all of this, if we go back to the question, is 99,800. That's essentially what we're saying. And so what we need to evaluate then is the sum from r equals x to r equals x plus 9. We've got 10 terms over here. So we've got 2r minus 1 cubed. Now, we normally want to start off at r equals 1. So for us to do that, if we start off at r equals 1, well, we've got the sum of the first from r equals 1 to r equals x plus 9 of 2r minus 1 cubed, and then we subtract the sum from r equals 1 to x minus 1, we want one below this, of 2r minus 1 cubed. So this is what we need to evaluate. And so if we were to evaluate all of this, well, if we use our answer to part A, n squared lots of 2n squared minus 1, we've got n squared. For here we'd have, well, let's just write out all of this in different colours. Here we've got x plus 9, and here we've got x minus 1. So if we use what we found in part A, instead of us having an n, we've got an x plus 9. So we've got x plus 9 squared lots of 2 lots of x plus 9 squared minus 1 minus, well, instead of us having an n, we've got an x minus 1 now. And then we've got 2 lots of x minus 1 squared minus 1, as we see here. And we need to tidy all of this up. So x plus 9 all squared, that's x squared plus 18x plus 81. And then inside this bracket, well, we've got 2 lots of this minus 1. So that will be we've got 2 lots of x squared, and then we've got 2 lots of 18x, and then we've got 2 lots of 81 minus 1, so that's 161, and then we subtract off the result of this, x minus 1 all squared, that's x squared minus 2x plus 1. And then here we've got 2 lots of this minus 1. So we subtract 2x, rather we've got 2 lots of x squared, 2 lots of minus 2x, and then 2 lots of 1 minus 1, which is just 1. So now we need to expand and simplify all of this. X times by 2x squared, that's 2x to the 4. X squared times by 36x, that's 36x cubed. X squared times by 161, that's 161x squared. Then we've got 18x times by 2x squared, that's 36x cubed. 18x times by 36x, well, let's just work that out. That's going to be 648x squared. And then we've got 18x times by 161, So that will be 2898x. And then we've got 1 times by, rather we've got 81 times by 2x squared, which is 162x squared. Then we've got 81 times 36x, so that's 2916x. And then we've got 81 times by 161, which is 13,041. And then we're going to multiply this by, well, here we've got x squared times by 2x squared, which is 2x to the 4. And then we've got x squared times by minus 4x, that's minus 4x cubed. Then we've got x squared times by 1, that's positive x squared. And then we've got minus 2x times by 2x squared, that's minus 4x cubed. And then we've got minus 2x times by minus 4x, that's positive 8x cubed. And then we've got minus 2x times by 1, that's minus 2x. And then we have 1 times by 2x squared, which is 2x squared. 1 times by minus 4x, which is minus 4x. 1 times by 1, which is 1. So let's see if we can tidy all of this up. If we were to tidy all of this up, rather here we've got a minus. Tidying this up, we've got 2x to the 4 minus 2x to the 4, that's 0x to the 4. And then in terms of the x cubes, 36 plus 36 minus 4 minus 8, that will be 80 x cubed. In terms of the x squareds, we've got 161 plus 648 plus 162 minus 1 minus 2, so that will be 960 x squared. In terms of the x's, we've got 2898 plus 2916 minus 2 minus 4, so that's 5820 x. And then we've got 13,041 minus 1, so that will be 13,040. So, what do we know already? Well, we know as well that if we add all these together, we get 99,800. And so, this result here the result over here, this is equal to 99,800. So we've got 80 x cubed plus 960 x squared plus 5820x minus 86,760. This is all equal to 0. And if we use our calculator feature to help solve this polynomial, if we type in the coefficients, Let's make sure we typed it incorrectly. So we've got 80 x cubed 960 x squared, rather here to make sure we've got a cubic. So we've got 80 x cubed 960 x squared 5820x minus 86760. It turns out we get x is either equal to 6 or minus 9 plus minus 9.87 etc. I. So therefore x equals 6 is the only solution. So because it's the only solution, what can we conclude from this? The smallest of these 10 consecutive positive odd numbers is, well, if we write down those odd numbers, we've got for our odd numbers 1, the odd ones rather, we've got 1, 3, 5, 7, 9, 11. We want the 6th one. So we get 11 as our final answer. Question number 5. The curve C has equation y equals the arc cosine of 1/2 x, where x is in between -2 and 2. For part A, we have to show that C has no stationary points. Well, for part A, we begin with what y is. Y is equal to the inverse cosine of x over 2. And so dy over dx, if we go to the formula book, the derivative for the arc cosine of x is -1 over the square root of 1 minus x squared. Well, here we don't have an x, instead we've got an x over 2, so we'll have to use the chain rule. So dy over dx is equal to -1 over 1 minus x over 2 squared, square rooted. So let's just make sure we're correct here with our derivative, and then we times by the derivative of what's inside the bracket, we times by 1/2. So that's what dy over dx is. And if we have a stationary point, that would imply dy over dx is equal to 0. So we have dy over dx, which is this. This is equal to 0. So we have 1 over 1 minus x squared over 4 square rooted which, if we work this out, rather, this is all equal to 0, because what I've done here is divided both sides by -1/2. And if I times through by the square root of 1 minus x squared over 4 square rooted, we end up with 1, which is equal to 0. This here is a contradiction. And so what we can conclude from then is C has no stationary points. Now for part B, the normal to C at the point where x is equal to 1 crosses the x-axis at the point A and crosses the y-axis at the point B. Given that O is the origin, we have to show that the area of the triangle OAB is 1 over 54 lots of p times by the square root of 3 plus q times by pi plus r lots of root 3 times by pi squared, where p, q and r are integers to be determined. what I've done over here is drawn a quick diagram of the curve C, the normal to C, and the tangent to C. And the normal crosses the x-axis at the point A, and it crosses the y-axis at the point B. And what we are required to do is find out the area of this triangle here. Now, what we have been given information about is we have the normal to C at the point where x equals 1. So we can find the equation of the normal, and we can also find the corresponding y coordinate. When x is equal to 1, y is equal to the arc cosine of 1 over 2, which is pi over 3. So that means the coordinate here is 1 pi over 3. We can also find out what dy over dx is. Now we've already worked out what dy over dx is. We work that out over here, so we replace the x with 1. So we have minus 1 over the square root of 1 minus 1 squared over 4 times by 1/2. It turns out we get minus 1 over root 3. What does this represent? The gradient of the normal is equal to the negative reciprocal of this, which is root 3. So what we can now do is find out the equation of the normal. We've got y minus pi over 3 equals root 3 lots of x minus 1. Remember, the normal passes through that point here. We can now find out the point of A and B. If we go back to the question, it crosses the y-axis at B, crosses the x-axis at A. So where it crosses the x-axis is when y equals 0. When y is equal to 0, we've got 0 minus pi over 3. This is equal to root x lots of x minus 1. So, minus pi over 3 root 3 equals x minus 1. So x is equal to 1 minus pi over 3 root 3, from which we can conclude A has coordinates. Well, the x coordinate is 1 minus pi over 3 root 3, and the y coordinate is 0. We can also find out the coordinate of B by setting x equal to 0. When x is 0, y is, well, we've got y minus pi over 3 equals root 3 lots of x minus 1. rather 0 minus 1. And so y is equal to pi over 3 minus root 3. So the coordinates of b then, we've got 0, pi over 3 minus root 3. Now let's draw out our triangle. We've got our triangle here. Now, if we take a look at what the value of pi over 3 minus root 3 is, that's negative. So we want the negative of this answer to make it a positive length. So, here's our diagram. We've got the height of this triangle being root 3 minus pi. So we've got here root 3 minus pi over 3. And we've got the base over here being 1 minus pi over 3 root 3. So we can calculate the area then quite simply. The area we've got 1/2 times by the base of the triangle, which is 1 minus pi over 3 root 3, and then we will multiply this by the height, root 3 minus pi over 3. So let's work all of this out. We have here 1/2 multiplied by, well, here we've got 1 times by root 3, which is root 3. So let's just write that out clearly. And then we've got 1 times by minus pi over 3, so that's minus pi over 3. And then we've got minus pi over 3 root 3 times by root 3. Well, that will just be minus pi over 3. And then we've got minus pi over 3 root 3 times by minus pi over 3. Well, that will be positive pi squared over 9 root 3. Now let's see if we can tidy this up even further. We have here 1/2 times by root 3. So that's 1/2. Well, that's just root 3 over 2. And then we've got minus 2 pi over 3 times by 1/2. So that will be minus 2 pi over 6. And then we will add on, well, if I rationalize, I've got 1 over 9 root 3. And then if I times this by 1/2, I add on root 3 pi squared over 54. And if I take out a 1 over 54 as a common factor, we've got 1 over 54 lots of, well, here we'd have 27 root 3 minus 18 pi plus root 3 pi squared. So therefore, P is 27, Q is minus 18, and R is equal to 1. Question number 6. The curve C has equation R equals A lots of P plus 2 cos theta, where theta is in between 0 and 2 pi. A and P are positive constants and P is greater than 2. There are exactly 4 points on C where the tangent is perpendicular to the line. We have to show that the range of possible values for P is 2, which is less than P, which is less than 4. Now here I've drawn a quick sketch of the polar curve. What we need to do is find the range, and for us to find the range will be in between this line and this line here. And these lines are parallel to the x-axis, if you like. So if we know that x is equal to r cos theta, we know what r is. That's a lots of p plus 2 cos theta. So we can then say, if we replace r with a lots of p plus 2 cos theta, x is equal to a lots of p plus p plus 2 cos theta lots of cos theta. And so what we can now do is find out what dx over d theta is. Dx over d theta, if we differentiate, well, we'll take an a outside, and then let's open up our brackets like so. We've got the cos theta multiplied by the derivative of p plus 2 cos theta, which is minus 2 sin theta, and then we add on p plus 2 cos theta multiplied by the derivative of cos theta, which is minus sin theta. So if we tidy all of this up even further, dx over d theta is equal to a lots of minus 2 sin theta cos theta minus sin theta lots of p plus 2 cos theta. Let's close this bracket here. Now what we need to do is set this equal to 0, and the reason we're setting it equal to 0 is because this line and this line are parallel to the initial line. And so if we have dx over d theta equaling 0, we've got this over here, which is all equal to 0. And if we expand what's inside the bracket and divide through by a, we've got minus 2 sine theta cos theta minus p sine theta minus 2 sine theta cos theta equals 0. So, collecting like terms, we've got minus 4 sine theta cos theta minus p sine theta. This is equal to 0. And if I factorize out a sine, we've got sine theta, lots of minus 4 cos theta minus p equals 0. So sine theta is either equal to 0 or minus 4 cos theta minus p equals 0. Now, from here we can say then sine theta is equal to 0 or cos theta is equal to minus p over 4. And so from here then, theta is either equal to 0 or pi. And if we have cos theta equaling minus p over 4, well then, from here, we have minus p over 4, which is greater than minus 1, and that's because cos theta is in between minus 1 and 1. And if we attempt to tidy this up even more, you will find p to be less than 4. And so, because we know p is also greater than 2, we've got 2, which is less than p, which is less than 4, for the range of values of p. Now for part B, we have to sketch this equation. R equals a lots of 3 plus 2 cos theta, where theta is in between 0 and 2 pi, and is greater than 0. Well, that's just this curve here. So the curve we see here is R equals a lots of 3 plus 2 cos theta. So let's just write that down for part B. See above. Now, for part C of the question, John digs a hole in his garden in order to make a pond. The pond has a uniform horizontal cross-section that is modelled by the curve with equation R equals 20 lots of 3 plus 2 cos theta, where theta is in between 0 and 2 pi, and R is measured in centimetres. The depth of the pond is 90 centimetres. Water flows through a hosepipe into the pond at a rate of 50 litres per minute, and given that the pond is initially empty, we have to determine how long it will take to completely fill the pond with water using the hosepipe according to the model. Give your answer to the nearest minute. Well, we know with polar coordinates, the area is given by 1/2 lots of the integral of r squared d theta. So the area that's given by 1/2 lots of the integral from 0 to 2 pi of r squared. Now we know what r is. That's 20 lots of 3 plus 2 cos theta. And then this is all being squared. We're going to integrate this with respect to theta. Now 20 squared is 200, is 400 rather, and if I multiply that by half I get 200. So I've got 200 lots of the integral from 0 to 2 pi of, well, 3 plus 2 cos theta all squared is 9, plus 12 cos theta plus 4 cos squared theta. And recognizing that cos squared is 1/2 lots of 1 plus cos 2 theta, we can simplify this even more. We've got 200 lots of the integral from 0 to 2 pi of 9 plus 12 cos theta plus 4 lots of 1/2 1 plus cos 2 theta d theta. So if I multiply the 200 into the bracket, we've got 200 times by 9 plus 200 times by 2. So we have the integral from 0 to 2 pi of, well, 200 times 9 plus 4 times 1/2 times by 1 times by 200, that will be 1800. And then we've got 200 times by 12, and that will be 2400 cos theta. And then we've got 200 times by 2 cos 2 theta, so that's 400 cos 2 theta. So if I work all of this out, we get 1800 theta. Rather, we get here, because if I add on the 4 times by 1/2 times by 200 to the 1800, I get 2200. So I've got 2200 theta plus 2400 cos, rather, if I integrate this I get sine. And if I integrate cos 2 theta, I get 1/2 sine 2 theta. And if I multiply that by 400, that means I would have to add on 200 sine 2 theta. And I'm integrating this between 0 and 2 pi. And if I substitute in my limits, for my upper limit, I've got 2200 times by 2 pi plus 0 plus another 0. And then for my lower limit, I have 0 plus 0 plus 0. So it turns out the area is 4400 pi centimeter squared. Now, if we were to find out the volume, we know the depth is 90 centimeters. So therefore, the volume is equal to 4400 pi multiplied by 90, which is 396,000 pi centimeters cubed. And if I convert this to liters, dividing by 1000, I get 396 pi liters. Now we've got that rate of 50 liters per minute, and from that we can find out the time. So the time is equal to 396 pi liters divided by 50 liters per minute, which is, if I work this out, 0.96 pi divided by 50, I get 24.88 etc. minutes. So to the nearest minute, we get 25 minutes. Now, for part D, we have to state a limitation of the model. For part D, the polar equation is not likely to be accurate. Question number 7. Solutions based entirely on graphical or numerical methods are not acceptable. Now, we've got figure 1 over here, which shows a sketch of part of the curve with equation y equals the inverse hyperbolic sine of x, where x is greater or equal to 0. And we've also got this straight line with equation y equals beta. The line and the curve intersect at the point with coordinates alpha beta. We're given that beta is a half times the natural log of 3. We have to show that alpha is equal to 1 over the square root of 3. So all we have to do is substitute in this point here into this equation. So for part A, we've got alpha beta. So we've got beta equals inverse hyperbolic sine of alpha. Now, inverse hyperbolic sine, if we go to the formula book, under the hyperbolic section, this is the result for inverse hyperbolic sine. And so we have the natural log of alpha plus alpha squared plus 1 square rooted equals beta. Now we know what beta is. That's 1/2 times by the natural log of 3. So we've got the left hand side remaining the same. However, for the right hand side, that's equal to the natural log of 3 to the power of 1/2, and if we antilog both sides, we would have alpha plus alpha squared plus 1 square rooted equals 3 to the power of 1/2. So we've got alpha squared plus 1 square rooted equals 3 to the half, which is root 3, minus alpha. So alpha squared plus 1 equals root 3 minus alpha squared. So alpha squared plus 1 equals 3 minus 2 root 3 alpha plus alpha squared. The alpha squared cancels on both sides. And if we tidy everything up, we've got 2 root 3 alpha equals 2, from which we can conclude alpha is equal to 1 over the square root of 3. Now for part B, the finite region R, shown shaded in figure 1, so that's this region here, is bounded by the curve with equation y equals inverse hyperbolic sine x, the y-axis, and the line with equation y equals beta. The region R is rotated through 2 pi radians about the y-axis. We have to use calculus to find the exact value of the volume of the solid generated. So for part B, the volume, that's equal to pi lots of the integral from mu to lambda of x squared dy. We're rotating about the y-axis about by 2 pi radians. Now, if y equals inverse hyperbolic sine x, then x is equal to inverse hyperbolic sine y. In other words, x squared is equal to hyperbolic sine y squared. So therefore, for the volume of R, we've got the integral from 0 to 1/2 times the natural log of 3 of hyperbolic sine squared y dy. That's what the volume of R is. So we've got the integral from 0 to 1/2 times the natural log of 3 of, well, here we need to be a bit careful. We have e to the power of y minus e to the power of minus y over 2. And then we're going to square this result. We've got dy here. So, well, don't forget we've got the pi here as well. So, we've got 1 over 2 squared times by pi, so that's pi over 4. And then we've got the integral from 0 to 1/2 times the natural log of 3. Now, e to the y minus e to the minus y all squared. We have e to the 2y minus 2e to the y e to the minus y plus e to the minus 2y dy. So we've got pi over 4, lots of the integral from 0 to 1/2 times the natural log of 3. We've got e to the 2y minus 2 plus e to the minus 2y, and that's because e to the y times e to the minus y is just 1, and we're timesing that by minus 2. So if we tidy all of this up and integrate, we've got pi over 4, lots of, well, integrating e to the 2y, we've got 1/2 e to the 2y. Integrating minus 2, we've got minus 2y. And integrating e to the minus 2y, we've got minus 1/2 e to the minus 2y. And we're evaluating this between 0 and 1/2 times the natural log of 3. So, we've got pi over 4, lots of, well, here, if I substitute in for my upper limit 1/2 times the natural log of 3, we've got 1/2 e to the power of 2 times by 1/2 times the natural log of 3 minus 2 times by 1/2 times the natural log of 3 minus 1/2 e to the minus 2 times by 1/2 times the natural log of 3. And then we subtract. For our lower limit, we've got 1/2 e to the 0 minus 2 lots of 0 minus 1/2 e to the 0. Now, 2 times by 1/2 is just 1. So we've got pi over 4, lots of 1/2 e to the natural log of 3 minus natural log of 3 minus 1/2 e to the natural log of 3 and then the result of this is 0. A half minus a half is 0, and then we subtract off 0. So if we tidy this up even further, we've got a minus there rather. We have pi over 4 lots of, well here, e to the natural log of 3 is just 3. So we've got a half times by 3 minus natural log of 3. And then we've got minus 1/2. Now e to the minus natural log of 3, that's just 3 to the minus 1. So if we tidy all of this up, we have pi over 4 lots of, well, a half times by 3 minus a sixth, that's 4 over 3. And then we subtract the natural log of 3. So this is my final answer. This is the volume of R. Question number 8. For the first part, the point P is one vertex of a regular pentagon in an Argand diagram. The centre of the pentagon is at the origin. Given that P represents the complex number 6 plus 6i, we have to determine the complex numbers that represent the other vertices of the pentagon, giving your answer in the form re to the I theta. Well, we've got one of those complex numbers, which is a vertex. For part I, if we find the mod of this complex number z, well, let's just say, let z1 equal 6 plus 6i, that means the mod of z1 is equal to 6 squared plus 6 squared square rooted, which is 6 root 2. And the argument of z1 is equal to the inverse tangent of 6 over 6, which is pi over 4. So we can conclude in mod arg form, z1 is equal to 6 root 2 e to the power of I pi over 4. Now let's draw a quick diagram to illustrate what the question's asking for. What we're saying is we've got a pentagon and we've got one of these roots, z1. We need to find the other vertices. Now the angle between each of these, from here to here we've got 2 pi, and if I divide that by 5, that means we've got 2 pi over 5 between each angle here. And what we need to do is find z2, z3, z4, and also z5. That's what we need to do in this question. And they are 2 pi over 5 away from each other. So if that's the case, what we need to do is add on from z1 multiples of 2 pi over 5. So we've got z equals 6 root 2 e to the power of I lots of pi over 4 plus 2 pi k over 5. Let's just emphasize where this came from. We've got 2 pi k over 5. And if we substitute different values of k in, we find the various roots. When k is 0, z1 of course is 6 root 2 e to the I pi over 4. When k is equal to 1, well, if we go to our calculator, and then if we enter into the complex mode, and if we go to the settings, to the complex settings, and then change it to the second type, we've got 6 root 2, and then if I press shift and then this, type in this as our argument. In other words, type in pi over 4 plus 2 pi over 5. And then here we've got different values of k which we're going to substitute in. K is 1. We get 13 pi over 20. So that means z2 equals 6 root 2 e to the power of I 13 pi over 20. K equals 2. We've got z3 equaling minus 19 pi over 20. So we've got 6 root 2 e to the power of minus I 19 pi over 20. K equals 3. We've got z4 equaling 6 root 2 e. And then here, if I change this to a 3, I get minus I 11 pi over 20. And k equals 4. z5 we get minus 3 pi over 20. So we've got 6 root 2 e to the minus I3 pi over 20. So these are our roots. Now for the next part, for part A, on a single arcane diagram we have to shade the region R that satisfies both the mod of z minus 2i being less than or equal to 2 and pi over 4 being less than or equal to the argument of z being less than or equal to pi over 3. So what I've got over here are the equations written down. Here we have a circle with center 0, 2, radius 2, and here we've got two half lines. So when we come to draw the required equations, we've got the circle here on the two half lines. Here we've got pi over 4, and here we've got pi over 3. So let's just add those angles on actually. Here we've got pi over 4, and here we have pi over 3. So the region we want everywhere inside the circle and in between the two lines. So here we've got the required region which satisfies both of these. So this is the first part. And now for the next part, we have to determine the exact area of R, giving an answer in its simplest form. Now, one way in which we can do this is to integrate using polar forms. So if we go back to the formula book, Here is how we find the area of a sector. Now, we require this shaded region here. And what we can do is find the polar equation of the curve and then integrate between pi over 4 and then pi over 3. So, to begin with, in Cartesian form, we have x squared plus y minus 2 squared equals 2 squared, which is 4. Of course, here the center is 0, 2. The radius of this circle, we know, is 2. So 2 squared is 4. Now, knowing that x is equal to r cos theta and y is equal to r sin theta, we can then see that in polar form, we have x squared, so that will be r cos theta squared plus y minus 2 squared, so that's r sin theta minus 2 squared. This is equal to 4. R squared cos squared theta plus r squared sin squared theta minus 4r sin theta plus 4 equals 4. The 4's cancel on both sides, and recognizing that cos squared plus sin squared is 1, we end up with r squared equaling 4r sin theta. So r is equal to 4 sin theta. This is the polar equation which we need to integrate. And remember, this is how we integrate. So therefore, the area we require can be found by integration. We've got 1/2 lots of the integral from pi over 4 to pi over 3 of r squared, so that will be 4 sin theta squared d theta. 4 squared is 16, timesing that by 1/2 we get 8. So we've got 8 lots of the integral from pi over 4 to pi over 3 of sin squared theta d theta. So we have 8 lots of the integral from pi over 4 to pi over 3 of 1/2 lots of 1 minus cos 2 theta d theta. So 1/2 times by 8 is 4. So we've got 4 lots of the integral from pi over 4 to pi over 3 of 1 minus cos 2 theta d theta. And if I multiply the 4 in and then integrate, we have the integral of 4, which is 4 theta, and the integral of minus 4 cos 2 theta, that will be minus 2 sin 2 theta. So we need to evaluate this in between pi over 4 and pi over 3. So substituting for our upper limit, we've got 4 lots of pi over 3 minus 2 sine of 2 times by pi over 3. For our lower limit, we've got 4 lots of pi over 4 minus 2 times by the sine of 2 times by pi over 4. So that's our lower limit. So what do we end up with over here? We've got 4 pi over 3 minus root 3 minus pi, minus and minus give a plus, and then we've got plus 2 here because sine of pi over 2 is just 1. And if we tidy all of this up, you can then see the area is pi over 3 minus root 3 plus 2 units squared. Question number 9. For part A, given that the mod of z is less than 1, we have to write down the sum of the infinite series 1 plus z squared plus z cubed, etc. Well, for an infinite series, the sum of that is given by here. We've got a, the first term, over 1 minus r, the common ratio. So, for part A, we've got 1 plus z squared plus z cubed, etc. The first term is 1, and then we're going to divide this by 1 minus the common ratio. To go from one term to the next, we multiply it by z. So the sum of this series to infinity is 1 over 1 minus z. Now for part B, we're given that z is equal to 1/2 times by the cosine of theta plus I sine theta. We have to use our answer to part A and Dumas theorem or otherwise to prove that 1/2 sine theta plus 1/4 sine 2 theta plus 1/8 sine 3 theta, etc. is equal to 2 sine theta over 5 minus 4 cos theta. Well, for part B, we're given z equals 1/2 times by cos theta plus I sine theta. If I substitute into the left hand side, we have 1 plus 1/2 cos theta plus I sine theta plus z squared. So we add on 1/2 cos theta plus I sine theta squared, and then z cubed, we have 1/2 cos theta plus I sine theta all raised to the power of 3. And then we could continue with our series, but what you'd find is all of this is equal to 1 over 1 minus 1/2 lots of cos theta plus I sine theta So let's tidy what we have on the left hand side using Dumas theorem. So let's just move this here. If we tidy what we have 1 plus 1/2 cos theta plus I sine theta. 1/2 squared is 1/4. And then if we use Dumas theorem, we have cos 2 theta plus I sine of 2 theta. And then 1/2 cubed, that's 1/8. And then here we've got cos 3 theta plus I sine of 3 theta. And then we could carry on, but what you'd find is this is all equal to, Now, what we're going to do here is multiply through the top and bottom by 2. So we end up with 2 over 2 minus cos theta plus I sin theta. Now, to make life easy for ourselves, we're going to rewrite this result on the right hand side. We're going to rewrite the result on the right hand side. So we've got brackets here and then a minus here. Because what we can now do is multiply this by the conjugate. We've got 2 minus cos theta plus I sin theta on both the top and the bottom. So if we continue to work all of this out, what you'll find is the left hand side is still the same, but what we have on the right hand side, we've got 2 times by 2, which is 4, and then we've got 2 times by minus cos theta, that's minus 2 cos theta, and then we add on 2 lots of I sin theta. And then on the bottom, we have a difference of 2 squares, 2 minus cos theta squared, minus, well here we've got I sin theta times I sin theta, so that's minus I squared sin squared theta. So let's simplify this even further. The left hand side is still the same, but on the right hand side, what we have, well, on the bottom we've got 4 minus 4 cos theta plus cos squared theta. Now here we've got minus I squared, which is positive 1, so we're going to add on sin squared theta. That's what we've got on the bottom. And on the top, we've got 4 minus 2 cos theta plus 2i sin theta. Now 4 plus 1 essentially, because cos squared plus sin squared is 1. We have this result here. This plus 1 comes from the fact that cos squared plus sin squared is just 1. So if we tidy all of this up, on the right hand side we would have 5 minus 4 cos theta. Of course 4 plus 1 gives a 5. Now if we go back to the question, we've got on the left hand side stuff involving signs only, which means we'd have to take a look at the imaginary parts. So comparing the imaginary parts, what we have here is a half sin theta plus a quarter sin 2 theta plus an eighth sin 3 theta, and then we could continue, and on the right hand side we've got 2 sin theta over 5 minus 4 cos theta. And that's exactly what we wanted to show. And now for the next part we have to show that the sum of the infinite series 1 plus z squared plus z cubed etc. cannot be purely imaginary, giving a reason for your answer. If we have something which is purely imaginary, then the real part of the sum is 0. So the real part is 4 minus 2 cos theta over 5 minus 4 cos theta, and we're saying this is equal to 0. That's why we set it equal to 0, as we see here. So we've got 4 minus 2 cos theta equals 0. Cos theta equals 2. Now, we know already cos theta must be in between minus 1 and 1. And because of that, we can say 4 minus 2 cos theta over 5 minus 4 cos theta cannot equal 0, which means the real part must exist. So, because there's also a real part, we can conclude that the sum cannot be purely imaginary.